In this section, we're going to be discussing what are called the limit laws. We have been talking about the limit from an intuitive standpoint, looking at tables and graphs. While tables and graphs can give us a good idea of what the limit may be, they cannot establish definitively what the limit is. For that, we need algebra. Algebra truly is the key to doing well in calculus at all levels. If you need to brush up on your algebra skills, you can watch my college algebra playlist and pick out the topics on which you think you might need review. Let me share my screen with you and we'll get started. We're going to be covering these learning objectives, learning the basic limit laws and using them to evaluate the limit of a function. We'll also use these laws to evaluate the limit of a polynomial or rational function, to take the limit by factoring or by using conjugates, and to evaluate the limit of a function using the squeeze theorem. Let's get started naming what the limit laws are. We're going to take two different functions, f of x and g of x, and we're going to let them be defined for all values of x in some open interval containing a, except they may not be defined at a. Then we're going to take two single finite real numbers, L and M, and we're going to let the limit of f of x as x approaches a be L, and the limit of g of x as x approaches a will be M. We're going to let C represent some constant number like 3 or 4.8 or pi. The following statements hold. These are the limit laws. We start with the limit of the identity function as we discussed in the last video. The limit of the line y equal x as x approaches a is just the value of x on the line, which is a. Then we have the limit of the constant function y equal to some c, like y equal 5, a horizontal line. The y value never changes, so no matter what value of a x gets close to, the y value stays c, so the limit is c. Then we have what are called the sum and difference laws. The sum law says that if I have two functions and I add them together first, and then I take the limit, I'll get the same value as if I take the limit of the first function, evaluate it and get L, and then take the limit of the second function, evaluate it and get M, and add those two together. In other words, what we often say is the limit of a sum is the sum of the limits. We have a very similar rule for the difference. When we have subtraction between two functions, and then we apply the limit to this new function, f of x minus g of x, we find that we get the same thing if we evaluate the limit at the first and the second, and then subtract their limit values. The limit of a difference is the difference of the limits. Now we have what's called the constant multiple or constant factor law. When we look at this law, it says that if I have a constant multiplied by a function, I'll get the same limiting value if I factor the constant out of the limit, and then I evaluate the limit of the function as x approaches a. So for example, we know from what we have studied previously that the limit as x approaches 3 of x is going to be 3. This says that the limit of 2x as x approaches 3 would be the same as 2 times the limit as x approaches 3 of x, which would give me 2 times 3 or 6. In other words, we can factor the constant out of the limit. It won't change the value of the limit. The product law and quotient law are allowed with limits, but they are not allowed with derivatives or integrals. This is an example of how powerful the limit is. We can do things with the limit we cannot do with the derivative or the integral. For a limit, the limit of a product is the product of the limits, which is a crazy idea. When we get to derivatives, you'll see this is not the case. But here, if we multiply two functions together and then take the limit, we get the same thing if we take the limit of the first function and multiply by the limit of the second function. We can do the same thing for a quotient with one exception. We need to make sure that the limiting value of the denominator function is not 0. Thou shalt not divide by 0. Now let's talk about the power law and the remaining laws. We have a power law, a root law, and a rational exponent law. The power law is also a very powerful one, which applies, of course, to limits, but not derivatives and not integrals. It says if I have a function raised to a power, I could pull the limit inside the power. Now, the idea behind this is that if you have the limit as x approaches 6 of x squared, I could instead rewrite this as the limit as x approaches 6 of x and then square it. I know from the first rule that the limit as x approaches 6 of x is 6. And this then would give me 6 squared, or 36 for the limit value. Now this works provided that n is a positive integer. Now, what if it's not a positive integer? The ones that follow take care of these other special cases, negatives and fractional exponents. Let's take a look now at the root law. The root law has to be broken up into cases because, as you know, if you put a negative under an even radical, the answer is not real. It exists, it's just imaginary. In that case, if n is even, then we need the limiting value to come out to be non-negative so that we can take the even root of a non-negative number. So if n is even, the limiting value has to be greater than or equal to 0, and the function value itself has to be greater than or equal to 0. Now, if n is odd, it won't matter, because if we take a cube root, then I know that it's going to come out to be whatever sign of the number that I put into it. So this applies no matter if it is an odd power or not. So, or if it is an odd power. So when I'm looking at something like this would be something like the limit as x approaches 2 of the cube root of x. I can rethink of this as the cube root of the limit as x approaches 2 of x. I know that the inside limit is going to give me 2, and this would give me, as a result, the cube root of 2. Again, I have to make sure if it's an even radical that what is under the radical is in fact non-negative. Now this will take care of many of the fractional exponents, but not all of them. What if you have some n and m value, they're both integers, and they're reduced and in lowest terms. So we won't write 2 over 4, we'll write 1/2. It could be positive or negative. This is going to deal with negative exponents, which move things to the base of the fraction, to the opposite location. Or if they're in the denominator, it moves them to the numerator. If I have the limit of f of x raised to the n over m power, then I can pull the limit inside of the power like this, and I'll get the limiting value raised to that power under these conditions. If m is odd, that means I have an odd radical, and then that means I've got n over m being greater than or equal to 0. This does not put it in the denominator. All right, because n over m is positive, it stays wherever it is. And then I can take L to the n over m power. What if m is odd, but it is a negative number, which will change the position? Well, then it's okay, provided that L is not 0, because we won't want to divide by 0. If m is even, if I have an even radical, I have to be more careful. If m is even and n over m is greater than equal to 0, I have to make sure that the limiting value is not negative. So it needs to be greater than equal to 0. If n over m is negative and I have an even radical, then it can't be negative and it can't be 0. So L's got to be strictly greater than 0. Now, these rules sound hard, but when you actually put them into play, it's usually fairly clear to students what the cases may be. Let's go ahead and take a look at example 1. We want to use the limit laws to evaluate this limit. And in each step, we want to indicate the limit law that we are applying. I've written out the steps for you. Let's go through them. First, in our head, since we don't actually write them all out when we're doing it, we split the limit of the product of the binomial and the square root into two different limits using the product rule. And then we take the limit of the first factor in our function and we split it again using the difference law. So we have the limit as x approaches 6 of 2x minus the limit of x approaching 6 of 1. Then over here, we apply the root law to pull the limit from outside the radical under the radical. In the next step, we're going to take the 2 and pull it out of this limit, applying the constant factor law. We're going to evaluate the second term in our first factor using the constant function law, which says that the limit of a constant function is always the constant function. So it gives us 1. Then under here, we're going to split the limit of the sum using the sum law into the limit of two different functions added together. Then again over here, we apply the identity function law to get the limit as x approaches 6 of x to be 6 multiplied by a 2. We bring down the minus 1. Now under the radical, we can again apply the identity function law and apply the constant function law again to come up with the values of 6 and 4. This ends up giving us 11 square roots of 10 as the limit value. From a practical standpoint, we do not go through all these steps in identifying them. What we do from a practical standpoint is we substitute the value of 6 into the limit function to see if we get one single finite real number. If we do, then that number is the value of the limit. Let's go ahead and take a look at example 2. In example 2, we again want to do what we just did by splitting it into different steps, indicating the appropriate limit law as we go. Go ahead and pause the video, work it out the way that I did in the previous one, then turn the video back on to see if you got what I got. Let's now examine the different laws used here. First, following the reverse of the order of operations, I'm going to split it into the quotient of two different limits using the limit law. Then I split apart the numerator using the sum law and the denominator using the difference law. Then I can split this first term where I have x raised to the third power using the power law and factor out the 3 using the constant factor law. This last one becomes the limit of a constant function, which as we know gives us the value of the constant function, here 5. Then I can evaluate the next one. Evaluating the limit as x approaches 1 of x, the identity function gives me 1 being raised to the 3rd power. On the next step, I can pull the limit inside the 2nd power, which will again give me the limit of the identity function as x approaches 1, quantity squared times 3, plus the 5. In the denominator, I've pulled out the 7 using the constant factor law, and then I evaluate the limit of x as x approaches 1 using the identity function law. Again, I then apply the identity function law here, and this leads me to negative 9/3 or negative 3. Let's now take a closer look at what happens when we substitute values. What we're really doing is substituting the value of x as it approaches a, the value of a, into our limit function. If we get a single finite real number, we're done. That is the value of the limit. So our first step is always to substitute the value of a into the function to see if we get one finite real number. These are the rules that we would have picked if we got to pick the rules, which makes them fairly easy to remember. If we have a polynomial function, all we need to do is substitute the value of a for x, and that will be the value of the limit. For a rational function where we're dividing one polynomial by another, we can, because they're polynomials, substitute the value of a in place of x in both the numerator and denominator, and whatever single real number we get will be the value of the limit, provided that the denominator does not turn out to be 0. Now let's go through and talk about the proof of this one right here. To see that this theorem holds, think about what a polynomial is. It is the sum and difference of terms with real number coefficients, c sub n, c sub n minus 1, multiplied by the variable, usually x, raised to a whole number exponent. It can be 0. Anything to the 0th power is 1, but otherwise it has to be a positive integer. If we take this polynomial and we take the limit of it, we can use the sum law to split up the different terms of the polynomial. Then we can use the constant factor law to pull the constants out of each limit. Then we can apply the power law to pull the limit inside of the power. This results in all of the limits really being applied to the identity function. And when we apply the identity function with the limit approaching a, we just get a. And this will give us the constant times a to that power, which is what we were trying to prove. Now this QED at the end signifies that we've reached the end of the proof. It's Latin for quota rat demonstratum, which means enough has been shown, or I'm finished. In grad school, we said quite enough, well, I'll let you finish it. Let's take a look now at examples 3 and 4. When we see a limit, the first thing we do is we substitute the value of what x is approaching into the limit function. If we get a finite real number, we are done. So first thing I'm going to try is substituting -2 for x. When I substitute this in, I end up with 3 times -8 plus 4 plus 7, which is a -24 plus 11. And -24 plus 11 is going to give me a -13. That is a finite real number. That's the value of the limit. As x gets close to -2, the y value gets super, super close to -13. In fact, it hits it. Let's look at the second one down here, where we have the limit as x approaches 0 of the quantity 1 divided by the quantity 1 plus sine of x. When we look at this one again, Even though it's not strictly polynomial divided by polynomial because of the trig function, we still approach it with the same technique. We're going to substitute 0 in place of x and see if we get a finite real number. If we do, that's the value of the limit. Substituting this in, I get 1 over 1 plus the sign of 0. The sign of 0 is 0, so I get 1 over 1 plus 0, or 1. That's a finite real number, which means that this graph, as we approach x equals 0, approaches the y value of 1. Let's now look at example 5. In example 5, we have the ratio of 2 lines, which makes it a rational function, ratio of 2 polynomials. Again, our first line of attack is always going to be to substitute the value of a in for x. This gives me 2 minus 7 times 1, all divided by 1 plus 6, which gives me 2 minus 7 over 7, or negative 5 sevenths. It is a finite real number. That's the value of the limit. We now want to turn our attention to algebraic techniques of evaluating limits. There are times when we plug in or substitute in the value of a, and we do not get a single finite real number. What we get instead is something called an indeterminate form. An indeterminate form is one that sometimes leads to one value of a limit and sometimes leads to a different value of a limit. In other words, there's no way of predicting what the value of the limit will be without additional techniques. We'll learn quite a few techniques to approach these later this semester when we study L'Hopital's rule. The two situations we're going to encounter today are 0 divided by 0 and infinity minus infinity. So if you substitute the value of a in and you get 0 divided by 0, this is an indeterminate form. The 0 in the denominator means the function does not exist there. Thou shalt not divide by 0. However, this is not the number 1. 0 is the only number that divided by itself does not give the number 1. 2 divided by 2 is 1, 3 divided by 3 is 1, but 0 divided by 0 does not exist. But the limit may exist, or it may not. It's indeterminate. The other one we're going to encounter is infinity minus infinity. As it turns out, and as we'll learn later this semester, there are different sizes of infinity. Some infinities are bigger than others. The number of rational numbers in the real number system is countable, and I'll show this to you later this semester. The number of irrational numbers is not countable. There are infinitely more of them than there are of rational numbers, even though they're both infinite groups. One of the sizes of infinity is larger than the other. Depending on which one is which, it could go to infinity, minus infinity, or maybe they're roughly the same size, and it ends up at 5, or 10, or negative e, or pi, or who knows where. It is indeterminate. We'll need advanced techniques in order to solve most of these. What we want to focus on in this section are some algebraic techniques that can help us resolve some of the situations of 0 over 0 or infinity minus infinity. The first situation is if we have a like factor in the numerator and denominator of something, like a rational function or the ratio of 2 functions. When we're looking at that, if we have a like factor, we know that the factor in the denominator will give us a value that it cannot equal or it'll be 0. And if that factor also occurs in the numerator, they cancel, but because they were there originally, it cannot be that value. Substituting in would give you 0 over 0. Let's look at this image and these two functions And I'm going to write this one larger so that it's easier to see. This is x squared minus 1 over x minus 1. Now, what we mean by a factored function is that this can be written as x plus 1, x minus 1, divided by x minus 1. Now, x cannot be 1. It is not defined at 1, because if you substitute it in, it gives you 0 in the denominator. Full stop does not exist undefined, but the limit may exist. If you have a factor that cancels, like this one, then what you find is that you have a hole in the graph at x equal 1. Not only that, but the y value there will be the y value of the reduced function. Plugging in 1, I'd get 2, and that is what it looks like it's going to hit. Notice that that function is the function we have on the left. These functions are identical to each other except at the point x equal 1. In the case of a canceling factor, where they exactly cancel one another out, then we do have a hole in the graph and the function still exists. So in this case, we factor out the particular function, and then we cancel whatever is common. We take what is left and we substitute the value of a into that. If we get a finite real number, we're done. If we get another indeterminate form, we look to see if there's something else algebraically we can do. Otherwise, we probably go on to L'Hopital's rule. Let's now look at example 6. The first step is always substitute the value of a into the function. In this case, the limit is approaching -3. When I substitute the value of -3 into the function, I get the following. I get 0 in the denominator, and I get 9 minus 12 plus 3, which is, 0 over 0. This means that the function is not defined there, but the limit could still exist. It may or may not. We don't know exactly what we have in the graph there. It could be either a vertical asymptote or it could be a hole. Let's take a look now by factoring the function inside the limit into x plus 3, x plus 1, which gives us 4x in the middle, and x plus 3, x minus 3. I can see that I have exactly the same factor in the numerator and denominator, and they cancel completely. Because they cancel completely, this becomes a hole in the graph. I cancel these out, and then I evaluate the limit at the reduced function. My 3 got a little carried away here. Which is going to give me -3 plus 1 or -2. And that will be the value of the limit. In other words, we definitely have a hole when x is equal to -3. Oh, that's what that was. I lost my arrow. There we go. All right. Another technique that can be applied algebraically to solve some situations of 0 divided by 0 is what's called multiplying by the conjugate. This often happens when we have a radical in either the numerator and or the denominator added or subtracted with another term. The first thing we're going to do always is substitute the value of a for the variable x. So in example 7, the first thing I try is the square root of 5 minus 1 minus 2 over 5 minus 5. I already know I'm in trouble because the denominator is 0. The numerator turns out to be the square root of 4 minus 2, which is 2 minus 2, which is that indeterminate 0 over 0 form. So in this case, I can't factor. Factoring doesn't make any sense here. even if I could factor the denominator, it's not going to cancel with the numerator. So instead, what I apply is another technique where I multiply by the conjugate of the one that involves the square root. So in this particular case, that would be the numerator. So I'm going to take my limit as x approaches 5 of the square root of x minus 1 quantity minus 2 over x minus 5. And I'm going to put numerator and denominator in parentheses and multiply by the radical plus 2. That's the conjugate. Now, I am not going to multiply by the conjugate of the denominator. I'm choosing only the one with the square root, and I'm multiplying by its conjugate divided by itself. This is just a form of 1, so I'm allowed to do this. Now, this pattern you know very well. This is the difference of two squares, x minus a times x plus a. Or as we saw previously, x minus 3 times x plus 3. When you multiply this out, the outside and inside products from distribution or the FOIL property are going to give you the same products but with opposite signs. So they cancel. What you end up with is the first squared minus the second one squared. This then is going to lead to the following. The limit as x approaches 5, and I'm going to write it out in more detail than I normally would, that times itself, minus 2 radical of x minus 1. That's the inside. I should do the outside first. Plus 2 radical of x minus 1. That's the outside of FOIL. Minus 2 radical of x minus 1. Minus 4. FOIL. In the United States, we use the acronym FOIL to represent distribution of two binomial-like objects. The denominator, we are not going to want to multiply it out. The one whose conjugate we did not take, leave it factored. Notice here that these two are identical except for the sign. And because they're identical except for the sign, they cancel out. We have not substituted the value of 5, so I have to keep writing the limit notation on every single step until I'm ready to do that. When I square the radical here, I end up with x minus 1. And then the inside terms cancel and I get x minus 4 over, leaving the denominator factored out. Can you see what's coming? When I simplify the numerator, notice that I got an identical factor to what was in the denominator, namely the one that was causing the 0 over 0 result. Now what I can do, because these are exactly the same, and I have one on top and one on bottom, they exactly cancel, so I know I must have a hole in the graph at x equal 5. This does not mean the denominator gets to jump to the numerator. This means that we are left with the placeholder of 1 in the numerator, and now we are ready to go ahead and resubstitute the value of 5 into the new reduced function. When we substitute it in this time, we drop the limit notation because we're substituting the value of a, and this gives us 5 minus 1 plus 2, which is 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, which is 1/4. The function is not defined at x equal 5, but the graph gets infinitesimally close to the y value 1/4 when x gets close to 5 from both sides. What if you have a complex fraction? Most students are not overly fond of fractions inside of fractions. So let's talk about how to deal with something like this. Our first step is always going to be substitute the value of a into the function. In this case, we have h instead of x. So we're going to substitute 0 in place of h. So I get 1 over a plus 0 minus 1 over a all over h, which is 0, which is going to give me 1 over a minus 1 over a over 0, which is the indeterminate 0 over 0. Notice that most of these have fractions involved. That's how you see what's coming. Now, occasionally we don't, and we'll learn to deal with those when we talk about L'Hopital's rule in section 4.8. For now, we're just going to focus on the ones that start out in fractional form. I got 0 over 0. Now, factoring is not really an option here, and there's no radical, so conjugate doesn't really make sense here either. So what could I try? Well, when in doubt, get a common denominator. So what we're going to do is we're going to take the small mini denominators, and we have quite a few of them. The mini denominators from the numerator and denominator, and we can think of h as h over 1, are a plus h, a, and the 1. So our lowest common multiple of all of those, or lowest common denominator, would be a times a plus h. We need an a plus h group and a single a factor by itself, plus the 1, but 1 can go on anything. So now what we're going to do is we're going to take the limit and we're going to multiply numerator and denominator. We go back to writing LIM because we have not substituted the 0 in yet. And we're going to put the numerator and denominator into parentheses. I like to write my denominator, or whichever part was not complex, as fully complex so I can keep straight. And we're going to take and multiply by the lowest common denominator divided by itself. I like to make the forms match, so I write it in complex form as well. This is the same thing divided by itself. This is equivalent to 1. We're allowed to multiply by 1 anytime, anywhere we feel like it. I'm going to distribute this over both terms in the numerator and distribute in the denominator. Just as before, I'm going to focus on the part that looks more complicated, which is the top, and I'll leave the bottom factored for now. So this gets distributed here and here. So I get a times a plus h times 1 over a plus h, which just gives me a. Then I have minus, and then the a's cancel on the second distribution, and I get a plus h, all divided by h times a plus h. I don't want to multiply out the denominator. I just want to get rid of the complex part. Now in the numerator, remember you need to distribute the negative. So if we distribute the negative, we end up with a minus h. This then means that I have the limit as h goes to 0 of negative h divided by h times a plus h. A single factor h will cancel another single factor h, but it will not touch part of a binomial factor with h in it. So this h cancels this h, which leaves a negative 1 in the numerator. This then gives me the following. I have negative 1 divided by a times a plus h. I still have the limit notation because I have not yet substituted in the value of 0 for h. I'm ready to do that, so I do that now, and I end up with negative 1 over a times a plus 0, which will give me a negative 1 over a squared. And that's the value of our limit. Let's take a look at example number 9. Example 9 focuses on a rational function, 1 over x minus 3, That is subtracting from it another rational function, 4 divided by x squared minus 2x minus 3. If I substitute the value of 3 in for x, what happens? Let's go ahead and do that now. I get 1 over 3 minus 3 minus 4 over 3 squared minus 2 times 3 minus 3, which turns out to be, I'm in trouble, 1 over 0 minus, well, this is 9 minus 6 minus 3. I'm really in trouble. If the numerator is a constant and the denominator is getting very close to, but not actually reaching 0, then it's approaching infinity. If I have infinity minus infinity, then this is an indeterminate form. I need to get it written together in one combined form so that hopefully something will cancel. In order to do that, I need a common denominator again. So I come back to the original and I factor the denominators of each term. Notice that they do have a factor in common, x minus 3. Then I multiply the first fraction by the x plus 1 over x plus 1, since it's missing that particular term, and that's going to give me the following. So let me write it out. I'm trying to get a common denominator. I have more than one term, so I need a common denominator. The second one already has the common denominator, and being lazy, I'm just going to write LCD. This then gives me the limit as x approaches 3 of x plus 1 minus 4 all over that lowest common denominator, x minus 3 times x plus 1. Simplify the numerator. I still haven't substituted, so I'm still required to write the limit notation. And notice that my numerator becomes x minus 3. This is the factor that was hidden in the beginning, but was creating a problem. Now I write out the full lowest common denominator, and I can cancel the like factors, becomes a hole in the graph. And now, when I evaluate the limit, I want to apply it to the reduced function, 1 over x plus 1. Which becomes 1 over 3 plus 1, or 1/4. Let's now talk about some, well, problematic limits. We're going to talk about one-sided limits that can cause problems. Let's think about the limit as x approaches 3 of the square root of x minus 3. Does it exist? How about the limit from the left of the square root of x minus 3, or the limit from the right? Let's look at the graph to fully understand why some of these limits exist and some do not. When we're looking at the graph, you can see that the limit from the right does exist, and it looks like it hits the y value of 0. So the limit from the right exists and it becomes 0. But I can't come from the left because the function, being a square root, is not defined on the left side of 3, which means as I approach from the left, there's nothing for me to track along. It doesn't approach. There's nothing there, which means the limit from the left does not exist. If 1 is 0 and 1 does not exist, then we know the two-sided limit does not exist. Let's now talk about piecewise defined functions. These are very interesting functions to investigate, namely at the points where they connect. So let's take a look at a piecewise defined function and talk about how to evaluate it. You'll see that this has 3 different pieces, and it connects at the value of -1 and in all 3 cases. So in all 3 cases, it could have been 2 different values, but in this case, it's all connecting at -1. So that's the most interesting place to look at, right there where it connects. And we want to know what the value of the limit of this function is as x gets close to -1 from the left, from the right, and the two-sided limit. Now, if you're looking at this from the left, you're looking at it from values of x that are less than -1. So you must use the function -x minus 2. So when we evaluate that limit, that's the one we have to use. So we would have the limit as x approaches -1 from the left of f of x would actually become the limit as x approaches -1 from the left of -x minus 2. Then we can use our substitute rule, and we come up with a -1 minus 2, which gives us a value of -1 from the left. What about from the right? From the right, we're approaching from values of x that are greater than -1, not equal to -1, greater than. For those, we need this bottom rule. So this will give us the limit as x approaches -1 from the right of x cubed. Then using our substitution rule, we get -1 cubed, which is -1. From the left and the right, it looks like it's going to hit -1. I don't even need to know what the function value is at -1. The left limit and the right limit agree. The limit is -1. In fact, this graph hits the value of 2 when x is -1. Let's take a look at this graph so that you can see and understand what happened. Here's a graph of the function on Desmos. Now, the only problem with Desmos is it's not good at showing where you have gaps or holes in the graph. It looks like it's plotting here at this corner down at -1, -1. If you click directly on it, though, it should show you that it is not, right? And let's see if I can get it right on it. There we go. It's undefined there, right? You have to click directly on the point to see that it's not defined. From the left, it looks like it hits -1. From the right, it looks like it hits -1. It actually hits 2, but the limit value is -1. Let's take a look at limits of the form some constant divided by 0. We've already seen this in one example today when we ended up with infinity minus infinity. So you know that when you have a constant value on top, and something approaching but not equal to 0 in the denominator, it must be approaching either positive infinity or negative infinity. Which one it approaches depends on the sign of the constant and which side of 0 it's approaching from. If we have a positive constant like 5 over something getting close to 0, but from the right side of 0, positive numbers, then the ratio of two positives would tell us it goes to positive infinity. If the constant's a positive number, like 5, but we're approaching 0 from the left side of 0, they're all negative y values, then this must mean that the ratio of these turns out to be negative infinity, so the graph goes down forever. If the constant is negative, we again combine the combination of signs. A negative constant, but approaching 0 from the right is going to give us negative infinity. And a negative constant approaching 0 from the left is going to give us positive infinity. Now let's take a look at examples 11 and 12. In example 11, the first thing we want to do is try to substitute in the value of a. The limit is as x approaches 1. So we substitute 1 to see if we can get a finite real number. Unfortunately, in this case, we get 3 over 0 being square. The square is important because it means that no matter what side of one I approach from, I'm going to be squaring it. So no matter what happens, it's going to be positive. And the 3 in the numerator is positive. So a positive divided by a positive and a constant over something approaching, but never quite getting to 0 has to be positive infinity. Let's take a look at the graph so that you can see why this must be the case. Right? As we approach 1 from both sides, you'll see that the graph is going off to infinity. This is what happens when you have an even power on the factor that is causing the 0 in the denominator. It will always be positive. It doesn't mean they'll always go to positive infinity, but it means that part of the ratio will always be positive. Now let's take a look at example 12. In example 12, we are again approaching the value of 1 for the ratio of 2 polynomials. Go ahead and pause the video, work these out, and then turn the video back on to see if your answer matches mine. Let's take a look now at what I got. When I substituted the value of a, which is 1, into the limit function, I ended up with 5 divided by 0. The 5 is always positive, which will want to pull it towards positive infinity. The 0 in the denominator means that because it's a constant divided by 0, it will go to infinity or negative infinity. The question is which one and from which side? If I think about the form of that equation, the 5 in the numerator is going to stay a 5. But the denominator depends on which side of 1 I approach from. If I leave the x squared plus x minus 2 here, and I visualize approaching from numbers to the left of 1, this might be 0.9 and 0.9. When I add them together, I'm going to get something that isn't as large an absolute value as the negative 2 is, which means that this is going to end up being a negative number. So I have a positive divided by a negative, which is going to pull it down towards negative infinity on the left side of x equal 1. If I take a look again at the same structure, but approaching from values of x that are greater than 1, then this might be something like 1.1 or 1.2 or even 3. And when I substitute them into this format, they're going to be larger in absolute value than the negative 2. So it's going to end up positive. And a positive over a positive approach to 0 is going to give me positive infinity, which means from the right side of x equal 1, the graph is going up forever. These two do not agree, which means the two-sided limit does not exist. Let's now take a look at the graph so you can see why this happened. When we look at the graph, you can see here at x equal 1 that as we approach the graph from the left side of 1, the graph goes down forever to negative infinity. From the right side of 1, as we approach 1, it goes up forever towards positive infinity. We have 2 sections left to discuss. We have the squeeze theorem and some important limits. Let's go ahead and start on the squeeze theorem. The squeeze theorem is a pretty important theorem in calculus, and it will come up more than once in multiple classes. The idea is relatively straightforward. The idea is if you have a function that is trapped between 2 other functions as it approaches 1 value, then the function that's trapped between the other 2 has to do what the outer 2 do. That's the rule. When you think about driving on a freeway, if you're on a 5-lane freeway and you're in the second from the right-hand lane, and you have an 18-wheeler on the right in the right lane, and you have an 18-wheeler on your left in the middle lane, and they decide they're going to go off towards I-25, then you're going off towards I-25 or you're going to have a wreck. You have to go where they go because you're trapped between them. Let's take a look at this graph right here. The idea is that as we approach A from both sides, the function g of x here in teal is trapped between the function of h of x, which is always above it as we get close to A, and is always above the function of f of x, which is always below it, close to A. May not be true out here or way up there, but close to A, I know that the function g is trapped between h and f. Well, if the function h and the function f have a limit value at A that is the same, well, then the one that's in the middle has to have the same limit value. That's the idea. Let's take a look at the formal statement of the squeeze theorem and then an example of a classic function used to demonstrate it. We're going to take three functions defined on some open interval around A that may be at A, and we're going to say that g of x is between f of x and h of x for all the values of x in that interval except maybe at A. Then we have the limit of f of x as x approaches A equals L, and the limit of the upper function, h of x, as x approaches A is also L. That means the top one and the bottom one agree. We're going to this number right here. Then the one that's between them also has to go to that number. The limit of g of x as x approaches A must be L. This works very nicely with sine and cosine functions because sine and cosine always oscillate between -1 and 1. That means that we can replace the trig function with a 1 or a -1 to trap a function with sine or cosine between two other functions that hopefully we can determine the limit of. Let's take a look at this limit right here. The limit is x approaches 0 of x squared times the sine of 1 over x. I know it's not defined at 0 because thou shalt not divide by 0, but the limit could still exist. I have no idea what x squared times sine of 1 over x is. I don't know what it looks like, but I do know that this is a sine function. Even though the argument is not simple like x, I know that it's sine, so it's going to go between -1 and 1. Which means that this function must be trapped between -x squared and x squared, replacing the sine function with -1 and 1. It's got to be above the graph of -x squared and below the graph of x squared. That means that if I can figure out what the limit of the outer two functions is as x approaches 0, I'll have the limit as x approaches 0 of x squared sine of 1 divided by x. And I do know what those limit values are. They're polynomials. I just substitute 0 in, and I get 0, which means that this function, though it's not defined at 0, it's infinitesimally close to the y value of 0 as x approaches 0. Let's take a look at what this one looks like so that you can have a better feel for what we're talking about. Here are my functions that you can see. The red function on top is the graph of x squared. The blue function on bottom is the graph of -x squared. And we can see that we have x squared sine of 1 over x oscillating between the two. Notice that as we get closer and closer to 0, it continues to oscillate, but it stays between the red and blue graphs. And because the red and blue graphs hit the value of 0 at 0, then we know the limiting value of that function, x squared sine of 1 over x, is also 0. Let's use the squeeze theorem to evaluate this limit of x squared times cosine of 1 over x. A squeeze theorem proof is very stylized. You write it in a very predetermined format. You start by saying the cosine of 1 over x has to be trapped between 1 and -1. That's a fact. And then you multiply each part of the inequality by x squared. Because x squared is strictly positive, you don't have to worry about reversing the symbols. And then you establish that the limit as x goes to 0 of -x squared equals 0. And that's also the value of the upper end function, x squared. And then you say, thus, by the squeeze theorem, it should read like a paragraph. The limit as x approaches 0 of x squared cosine of 1 over x equals 0. Okay. Now, if you had tried to plug it in, what would have happened? You would have had 0 here for the x squared times the cosine of 1 over 0. But this is infinity, so what does that mean? Well, we don't know. If we don't know, think of it as indeterminate, meaning try another method. The squeeze theorem is a good method for sine and cosine related functions. Now we want to talk about the last section in this particular video, which is some important trig limits. We'll learn better ways of evaluating the ones on the bottom when we talk about L'Hopital's rule. For now, you can just memorize them. The first two you can get from straight substitution. The limit of the sine of an angle as the angle approaches 0, well, you just substitute 0 for the angle and the sine of 0 is 0. Done. The limit of the cosine of an angle as the angle goes to 0 is 1. Again, if you substitute and get a finite real number, you're done. This one is more difficult because if you substitute 0, you get the indeterminate form of 0 over 0. But in this case, none of our techniques will work. Not factoring, there's no complex fraction, there's no radicals I can solve with multiplying by a conjugate. I'm just stuck. And notice that this one and this one are essentially the same, except this is the reciprocal of this. But as we know, we can split the limit. And we know that this means that I could have written this one here as the limit as theta approaches 0 of 1 over the sine of theta over theta. Remember, the denominator of the denominator is actually in the numerator, or the bottom of the bottom is the top. And then I can apply the quotient rule to split it into the limit of 1 and the limit of sine theta over theta, which I know is 1. And 1 over 1 is 1. So both of these give me the value of 1. This next one is a little bit different in that it has two terms in the numerator. The cosine of 0 is 1, so 1 minus 1 will give me 0 over 0, which is indeterminate. But again, none of our techniques work. This, however, comes out to be 0. We cannot take the reciprocal like we did here, because the reciprocal of 0 gives us 0 in the denominator, and thou shalt not divide by 0, at least not in my class. Let's now take a look at examples 14 and 15. These are a little bit tricky when you first start out. In fact, they're a little bit complicated. It's mostly an algebraic process of working out what these should be. Let's focus on 14 first and leave the other limits up above so we can refer to them. This part here looks like this one here. But This part here looks like one of these two. Well, that's kind of a problem. I've got a mixture of two different types. What am I going to do? Well, I'm going to pull them apart. I'm going to rewrite this. And again, you should plug in the value first to see what you get, but I'm going to go ahead and do it real fast in my head and tell you you get 0/0, which is indeterminate. So the first thing I'm going to do is I'm going to write this as 1 minus the cosine of theta over 1 times the limit as theta goes to 0 of 1 over the sine of theta, right? Or actually, let's leave the limit out for now, and we'll just put 1 over sine theta. Now, if I only had a theta in the denominator here, and I only had a theta in the numerator here, I'd be good to go. Well, a theta on top and a theta on bottom sounds like the number 1. So let's multiply this by the number 1 in the form of theta divided by theta. I'm going to take the denominator theta, and I'll write it under the 1 minus cosine of theta. And then I'm going to take the second theta in the numerator and write it in the numerator over sine theta. Then I can apply the product rule and split this into the product of two different limits. This then will give me the limit of the first factor multiplied by the limit of the second factor. I know from what I have up above that the first one becomes a 0 and the second one becomes a 1, which gives me 0 times 1, or the value 0. Whatever this function looks like, it gets very, very close to the value of 0 as theta approaches 0. It's not defined there, but it gets very close to it. We have one more example to work, which is this one here. I'm going to get you started, and then I want you to pause the video and work out the example on your own. To get started on this one, we again substitute the value of theta, which gives us sine of 0 over sine of 0, which is 0 over 0. I always want to see the 0 over 0 to know for sure that you understand it's an indeterminate form. Be sure you write that down. Then what I want to do is I want to look at the limit. Now this has a 2 theta and a 5 theta. Now that's a little bit of a problem. But as theta goes to 0, 2 theta also goes to 0, and 5 theta goes to 0, because the constant times 0 is still 0. So I want to split this apart into two different ones. And I want to have sine of 2 theta up here, and 1 in the denominator, and 1 and sine of 5 theta in the denominator here. Now, I can't quite do what I did last time because the arguments don't match. In order to apply the rule, I have to have 2 theta here and 5 theta here. But I can multiply by 1 in the form of 2 theta over 2 theta and 5 theta over 5 theta. I'm going to take this 2 theta here and move it in the denominator to join that one. Then I'm going to take the 5 theta here and move it in the numerator of that one to join that one. You'll see that you're going to get some cancellation. Go ahead and pause the video and work it out. Okay, let's see. What did you get? So the next step that we need to do is to rewrite it. So we have the limit as theta goes to 0 of sine of 2 theta over 2 theta times 5 theta over sine of 5 theta. But I still have a 2 theta And a 5 theta I didn't use. This needs to be in the denominator. Well, the thetas are going to cancel each other out, and I get 2/5. Well, 2/5 is a constant. I can pull that to the front. And then I can evaluate each limit individually. This goes to 1, this goes to 1. So I end up with 2/5 times the limit as, well, 2 theta goes to 0, of sine of 2 theta over 2 theta. Remember, as theta goes to 0, 2 theta goes to 0, times the limit as 5 theta goes to 0, because as theta goes to 0, 5 theta goes to 0, of 5 theta over sine of 5 theta. And that means this goes to 1, this goes to 1, and I get 2/5. In the next video, we'll discuss infinite limits and limits at infinity.